Well, this is the second time I'm doing this problem. I just realized that I did the whole thing without being on record. So hopefully this time will be the charm. So here we are. This is the heart and soul of energy methods. This is a very important problem to understand, particularly the work energy approach. Um, so we're going to do this twice. Once on the left with ordinary kinematics, once on the right with work and energy. So first I need a cartoon, as I always do. This is way more than 10 degrees. I'm going to leave theta as an unknown here. If I drew a 10-degree angle, nobody could read it. So here I am. At any point, my penguin is going to be there. If I'm going to consider a free body diagram, so there's the penguin. I'm going to have a normal force going perpendicular to the slope. I'm going to have gravity going downward. And I'm going to have a frictional force going back up the slope. Now, in this problem, it makes sense to choose a coordinate system that is aligned with the slope. So I'm going to choose y to be that way, x to be that way. And that means that I need to decompose the gravitational force into components. Now let me label all of my things I have just drawn. So this is the normal force. Whoops, wrong tool. This is the normal force. This is the weight. Its components are, that one is mg sine theta. This one is mg cosine theta. And finally, this is the force of friction, which I know is mu times the normal force. And of course, mu is the thing I want to know. Just to be clear about my symbols, this 12 meters I'm going to call L, this 10 degrees I will call theta, and this velocity I'm going to call v final. So in this problem, I'm going to take a two-part approach. I know that I can use F equals ma to relate the forces to the acceleration. And then I'm going to use kinematics to relate A to the change in velocity and the length. Since there's no time that appears in this problem, the kinematics relation that I'm going to want to use is v final squared minus v initial squared equals 2a delta x. All right. So let's get started and dive in. So in the using F equals ma, you know that since I have things happening in both x and y, I need to think about both x and y directions. So in y, let's see, looking at my force diagram, I just have that the normal force minus mg cosine theta equals may, which is 0. And that tells me straight away that the normal force is mg cosine theta. Shouldn't be surprised by that. We've seen that pattern before. And then in x, I know, let's see, I've got friction going up, gravity going down. So I know, and I'm going to go ahead and substitute in mg cosine theta for the normal force here. So that tells me that, let's see, friction goes back up the ramp, so minus mu mg cosine theta plus mg sine theta equals max. And all of the m's cancel. So I get an expression for ax here. So now I have my relationship between acceleration and the coefficient of friction. My kinematics, remember I had that, I'm going to zoom in a little bit because I'm running out of room. I know that Vf squared minus V naught squared equals 2a delta x, but I know that V naught is 0. So that gives me, substituting in my relationship for A, that gives me Vf squared equals 2a delta x. So I have 2 times that thing from above minus mu g. Actually, I'm just going to write the 2 in front of every term. So I get minus 2 mu g cosine theta plus 2 g sine theta, and all of that is multiplied by delta x, which is L. So I'm going to do that. I guess we can afford that. So let me now multiply all of that out. I have Vf squared equals minus 2 L mu g cosine theta plus 2 L g sine theta. And what I wanted to do was to solve this for mu. So I'll put mu on the other side. Doing the algebra, this gets me mu equals two Lg sine theta minus Vf squared all over. It's all the stuff that multiplies mu, so 2Lg cosine theta, which when you put in the numbers is equal to about 0.107. So that's the kinematics approach. Now let's do the work energy approach and compare. Again, I want to start by drawing a picture. Label my angle, and I'll label now my initial and final states. I'll do these in red because they're so important. The work-energy theorem is all about thinking about what kind of work is done as I go from initial to final. So the work-energy theorem says that the change in kinetic energy is the work done by all forces, which here is the work done by gravity, plus the work done by friction. We know that gravity is going to do positive work and friction is going to do negative work. So remember that work is the dot product of force with displacement, which means the force times the distance displaced parallel to that force. So if I think about my forces, right, friction goes up the ramp. So the displacement parallel to friction is going to be minus L. It's minus L because they are in the opposite direction. But now thinking about gravity, only the displacement up and down counts for this. So here, the displacement parallel to gravity is going to be L sine theta, just the vertical piece. So this means that the work done by gravity is going to be the size of the gravitational force times the distance displaced parallel to that force. The work done by friction is going to be the size of the frictional force, which from before I know is mg cosine theta. So we're going to use that. It's going to be mg cosine theta times minus L. So putting these ideas together, the change in kinetic energy is going to be 1/2 mv final squared minus 1/2 mv initial squared. Of course, I know that term's 0. Equals, let's see, I just add up the work on the right side. So I have mgl sine theta minus, oh shoot, I forgot the force of friction was mu mg cosine theta. That's important because mu was the whole thing I'm solving for. Sorry about that, folks. Mu mgl cosine theta. So now what's left? All I need to do is solve for mu, because I know that that term canceled. So again, I can also cancel the m's that appear in every term in this equation. We weren't even given a mass, so the answer can't depend on it, right? So this is going to give us, in the end, doing algebra, that mu is gl sine theta minus 1/2 v sub f squared all over gl cosine theta, which again is around 0.107. So what's the point here? We got the same answer with both methods. Notice that these two fractions down here these two symbolic answers, they differ only by a factor of 1/2 in both numerator and denominator. And we should expect that they should be the same, because if you remember when we derived the work-energy theorem in class, we started by using this kinematics relation. So the algebra in the end winds up being very similar. The answer, of course, is the same because both methods are valid. But the difference is in the mindset. In the approach on the left, the one with kinematics and Newton's second law, we asked, what is the acceleration of the penguin at one moment in time? And once we found that, we related the acceleration to the forces, and then we related that acceleration also to the change in velocity. So we had this intermediate quantity we were thinking carefully about called acceleration. In the work-energy theorem, I didn't need to do that. I didn't need to break anything into components. although I did need to think carefully about what the displacement was, whoops, what the displacement was parallel to each force. That is an important idea. When I'm calculating the work done by gravity, the displacement used here is not the entire distance moved, it's only the distance moved vertically. But since friction is exactly anti-parallel to the motion, we used minus L for the displacement there. Then the work-energy theorem emphasizes how much work is done as I go from initial to final states. And then once I've thought carefully about the work done by various things, then I can just write down the algebra corresponding to the work-energy theorem and solve. Notice that on the right there are no vectors. I did have to think about components of forces parallel to motion, components of motion parallel to forces, but I don't have separate x and y work-energy theorems. There is only one work-energy theorem because work is a scalar. I hope this was useful. This problem in particular, along with number 4, are very important for you to understand. I would say that number 4 is probably the most important problem. But if you haven't understood this explanation, go back and study a bit, maybe watch this video again before going on to number 4. This is the second time I've recorded this, and now I will record number 4.